As you start thinking about 2.9 uniform motion, I really want you to think about several possibilities that you will have to face as you start solving these kind of problems. And the first scenario that I want to discuss about briefly is the scenario where let's say that you have two objects. Could be a plane, could be a ship, it could be cars, whatever. But starting at the same point in the center, going in opposite directions. Okay, and at some time later, this is still at the where they started off. At some time later, object B is right here, and possibly object A could be right here. They are at some distance apart. This is the distance of object B, and this is the distance of object A. So you want to find out what the distance apart is. All you have to do is add these two together to find the distance apart. Okay, so that's one scenario where you start at the same place, go in an opposite direction. Another scenario now that I want you to think about is when you have two objects coming together. They start at two opposite ends, but they are heading toward some point. That means they meet at some point in time. So they're going toward each other, and then at some point later, A and B will be together, face to face. I mean, this case is called the, collision case, or whatever you want to call it. But then, if you think about this, the distance that object A travel, which is dA, and the distance that object B travel will still give you the distance when they were first apart, right? So this is very similar to the first case, even though they're coming together, but you know that initially they were at some distance apart. So very similar setting. Either they're going away apart or they're heading towards each other. It's still the same setup. Distance of object A plus the distance of object B will give you the total distance apart. Okay. Now another scenario that I want to talk about, and this is most likely something that you will see, is the chasing scenario, where in the first case, object A and object B are at the same starting point. Okay, here's the first scenario, and then object A, let's say object A will get to go first, while object B waits behind the starting point, because object A travels slower and object B is traveling faster. So basically, A will get to go first, and B will wait for some time, and then it will try to catch up with object A. Okay, so when B is starting to take off, object A will be far ahead. However, because B is traveling faster than A, you know that at some point in time, it will catch up with A. When we say catching up, it means that it's be neck to neck with A. So for it to catch up, as you can see here, B needs to cover the same distance as A. So for that, we can say that the distance that object A cover will be the same as distance B. So this is another likely scenario that you will face. So depending on the kind of scenario, I really want you to go back and revisit, and this is the basic structure on how to set up your equation. Okay, so kind of keep that in mind. Alright, so I'm going to cover 2.9 weighted average problems again, but this time I'm going to focus on uniform motion. Okay, so with that, I'd like to introduce once again another model, just similar to the investment problems, but this time we're using the distance model. Okay, so here we go. Distance equals rate times time. Many of you have heard of this, the DRT, before, probably in your science class as well, and we are going to be using this for today. Now, for those of you who don't know what D or RT is, let's define that. D is the distance travel. Oh. And of course, R would be your rate or your speed, and the T is your time. Okay, now don't forget, you want your time to be consistent with your speed. Okay, we'll talk about consistencies in a minute, but for instance, okay, let's say that my car, I have a car, travels at 50 miles per hour, okay, and I'm driving for 3 hours. I want to find out how far did I travel. So in this case, I can certainly use the distance model right here. D equals R times T, and I simply plug in what I have. This is the rate, which is my speed, and this is the time. Okay, so I plug in the value, which means I have 50 times 3, which ends up being, well, let me just kind of show you the unit here, 50 miles per hour, right? And this is 3 hours, okay? And the hours cancel out, so we end up with miles. So therefore, we have 150 miles traveled. Okay, so you can kind of see what the distance model is all about, because this is what we're going to be using throughout the problem. So let's take a look at this. Two jets leave St. Louis at 8 a.m., one flying east at the speed of 40 kilometers per hour, greater than the other. Now, I didn't say that jet is flying 40 kilometers per hour. That's too slow for a jet. You got to be reasonable too, right? This says the speed is 40 kilometers greater than the other. Okay, so we have two jets leaving. So once again, you need to identify that we have two different objects, which is traveling west. So one is traveling east, one is traveling west. So you kind of see the scenario. Here's I'm trying to draw my plane. I know it's not a good looking plane, but this is called jet A, this is jet B. They're going away from each other, so at some point in time, based on this, at 10 a.m., the planes are 2,480 kilometers apart, okay, because they're traveling away from each other. And then basically I stand on the ground, take a snapshot of that at exactly 10 a.m., and I realize that these two jets are 2,480 kilometers apart. And then I need to find their speeds. Okay, I don't know their speeds. Now, so how do we set this problem up? Very similar to the investment problem. What you do is you want to create a table once again, just like this. Differentiate between jet A. Okay, so this is jet A and jet B. And since we are using the D equal RT model, so let's write it. The rate times the time equals to the distance. Okay, so we have 3 columns this time. Okay, so let's take a look at the rate or the speed of jet A. Do we know the speed of jet A? Well, according to this, let's say jet A is the one traveling west, and then jet B is the one traveling east. Okay, so based on this one right here, we don't know the speed of either jets, but we know that the one that's flying east, which is jet B, travels 40 kilometers greater than the other one. That means jet A is traveling slower than jet B, right? But since we don't know what the speed for jet A is, let's declare that as x. But then for jet B, we know that jet B is traveling 40 kilometers greater than jet A. So can we just say that it is x plus 40? Because we know that it is 40 kilometers greater than jet A, right? Now, do we know about the time in this case? So let's take a look. It says leave at 8 a.m. and at 10 a.m. So that means how many hours later? 2 hours later, right? So we have the time as well. We start from 8, and we take a snapshot at 10. So 2 hours later for both planes. Okay, and we know that the model says, okay, to find a distance, we just multiplied R and T. So we have 2x right here, and this is 2 times x plus 40. Okay, and so now we can just go and focus on this last part. It says right here that at 10 a.m. the planes are 2,480 kilometers apart. That means the total distance traveled from both planes. If this is the distance traveled for jet B, and this is the distance traveled from jet A, we need to add the two together to get the total, right? So in other words, we get the distance of jet A plus that to the distance of jet B will give us a total of 2,480 kilometers. So as you can see, we don't need the rate column anymore because we just have one variable to deal with. So it's just going to be 2x, which is the distance of jet A, plus the distance of jet B, which is right here in this column, 2 times x plus 40, equals to the total distance of 2,480 kilometers. Okay, so we do some cleaning up work here. It's just going to be 2x plus 2x plus 80 equals to 2,480. This combines will become 4x, right, plus 80 equals to 2,480. If we continue solving for this, we'll subtract 80 both sides. We will have 4x equals to 2,400. We'll divide it by 4 both sides, like this. X will simply be 600 kilometers per hour. So it makes sense for a jet to travel this fast. Okay, so that means x is the speed of jet A, right? Based on our table anyway. And then so to find the speed of jet B, we just have to add 40 to it because we acknowledge that jet B is traveling 40 kilometers faster. So that means to find it, we just take the speed of jet A plus 40, which is 600 plus 40, will give us 640 kilometers per hour. And this is for jet B. And we got our answer that way. Okay, so with that, please work on this particular problems. Try this. This is also one of the homework problems in the worksheet, so just go ahead and work on that for practice. You can refer back to the previous example as well. Continue uniform motion with this particular example of a small plane and a jet. Basically, the small plane takes off first, and then the jet leaves 30 minutes later to catch up with the small plane. Okay, and if you're trying to do a catching up kind of gig, you need to make sure that your speed is faster than your opponent in order for you to catch up. So pretend here that, of course, the jet and the small plane, I'm just going to go ahead and use the letter S for the small plane, and the jet, I'm going to use the letter J for the jet. They are at the same starting point, but of course the small plane gets to take off first. So, and while the jet is waiting to say, you know what, since you're slower, I'm going to let you go first. So this is the first snapshot of what's going on. This small plane takes off first. Okay, now 30 minutes later, the jet starts to take off. Okay, and by that time, as you know, the small plane is still far ahead, right? So this is the second snapshot of what's going on. But at some point in time, in order for the jet to catch up to the small plane, don't you agree that for it to catch up to the small plane, the jet has to be right there, side by side with the small plane, in order for you to say, hey, yeah, the jet is all caught up, right? So notice that the scenario of the third case here, that in order for the jet to catch up to the small plane, the jet must have covered the same distance as the small plane in a shorter amount of time. Reasons? Because remember, the jet was still at the starting point while the small plane was flying. Okay, so I mean it had less time to travel, yet because of its high speed, it's able to catch up to the small plane anyway. So I want you to keep that in mind as we look through this problem. Okay, so let's draft this problem here. Go ahead and get a piece of paper. So let's take a look at this problem once again. A small plane leaves an airport and flies north at 240 miles per hour. A jet leaves the airport 30 minutes later and follows the small plane at 360 miles per hour. How long does it take the jet to overtake the small plane? So I really want to encourage you once again to use the DRT model, right? So create yourself a table just like this and put 3 columns in there, because you have the rate times the time equals distance, right? And of course you have the small plane to compare, so I'm going to go write small plane for that one, and I also have the jet to compare. So as we read through the problem, we know that the jet is flying at 360 miles an hour, so I'm going to go ahead and write that value in there, miles an hour, under the rate. Rate is for speed. Small plane is 240 miles per hour. Now, if we look at the time, we don't know how long the small plane spent flying. Same thing for the jet, right? But if you notice anything about it, it says that the jet leaves 30 minutes later than the small plane. So since we don't know the small plane's speed, a time, we can certainly declare a variable for it. So let's say the small plane spent S amount of time in the air, and since the jet left 30 minutes afterwards, it has 30 minutes less to travel. So as you know, it's less less means minus. So you can certainly say that it has less time than the small plane's time. So that means it's the time of small plane minus the 30 minutes. But one thing I need to mention is, don't forget, since we're talking about hours here, you got to convert your minutes to the same units as hour. And the way that we do it is by taking the minutes, put it over 60, because we know that an hour has 60 minutes, and we reduce that to be an hour and a half, right? Sorry, 1/2 in an hour. So that means right here, instead of putting 30 minutes, you should be putting 1/2 to represent half of an hour, okay? Now we just go ahead and multiply it right across. You have 240 s, which is the speed of the small plane, the distance of the small plane, and we know the jet's going to be 360 times s minus 1/2. Okay, so we want to focus on the distance column right here, and remember what I showed you about the third case, where in order for the jet to overtake, or at least be able to see the small plane, it has to be right up there with the small plane. To be right up there, it must have covered the same distance as the small plane. And the word same in our case means equal. So that means the distance of the small plane at that point in time has to equal to the distance of the jet. So all we have to do is just set the two distances equal to each other. And there you have it. You have yourself an equation, and we can start solving for s. So let's go ahead and solve for that. We distribute 360 into each term inside. We got 360s, and half of 360, as you know, is going to be 180, right? Well, 360 times a half. And we can combine like terms here by moving 360s over. You got yourself 120s equals to, negative 120s equals to negative 180. And of course, if we divide it by negative 120 both sides, s gonna give you, well, let's divide it, 120, 180, cross out the 0 because we don't need it. 12 goes into 18 one time. That's going to give you a 6. 0, 12 goes to 65 times, right? So that's 1.5 hour, 1.5 or 1.5 hour. Okay, so that means 1.5 hour, this small plane spent 1.5 hour in the air, and to solve for the jet, all you have to do is just go ahead and take half an hour off of that. So s minus a half, or 1.5 minus a half, which is 1 hour. Okay, so we got the small plane's time, we got the jet's time. This is for the jet. So that means an hour later, after waiting for half an hour, the jet will overtake the small plane based on the problem. So notice it says right here, how long does it take the jet to overtake the small plane? It took the jet 1 hour exactly. Okay, so what I want you to do is to go ahead and try this next problem on your own. Try to set up a table and then try to solve. Don't forget about the 20 minutes. You can't leave that in minutes, because notice that the other units are all in hours. So you got to do a conversion of minutes to hours. Remember, we have 60 minutes in an hour, so we can certainly convert that. And keep that in mind.